Okay, so hopefully you're following along. Random people who stumbled on this channel, you're not following along, but for my students, hopefully you had a chance to do these warm-up questions, which led to these key concepts here on this page, page 9 of the notes. So some properties of a confidence interval for P. And as we saw in the exercise, well, the higher... Oh, I finally figured out why I'm leaning, because I'm not centered, but then... Okay, wait, here we go. I'm right-handed, I can do this. I'm sorry, y'all are just gonna have to deal with my awkward diagonal shoulders, and I think maybe only I can tell. Oh well. Well, anyways, the higher the confidence level, the wider the interval, the larger the sample size, and this one we can think about it intuitively. We know that larger samples tend to have smaller variability. So the larger the sample, the more narrower, the smaller, the lesser the interval. So increasing our sample size will decrease the width of the interval, increasing the confidence level will increase the width of the interval, and the further p hat is from 0.5, the smaller the interval. And this one, for calculus people, you know that if we take the derivative, we would figure out that the maximum value would be at 1/2, but even some algebra skills here, maximizing this area. The reason 0.5 is the magic number is because if I take 0.5 times 0.25, I get 0.25, and I don't know if that cut me off there, 0.25, and then it's going to go away. But then if I do 0.4 or 0.6 in either order, that's going to put me at 0.4. And then what if we went extreme? What if I did 0.9 and 0.1? Well, then that would put us at 0.09. So we can see that here 0.5 is actually going to maximize the value here in the numerator. So that'll just make it smaller. So the closer it is to 0.5, the larger the interval. The further from 0.5, the smaller the interval. And so now let's go ahead and look at some examples here to estimate the proportion of faculty at Butler University who drive an American manufactured sport utility vehicle. A random sample of faculty is selected. For each of the following combinations, which variable condition would result in a narrower confidence interval? So here, I'm just going to do this really quickly. If we want a smaller interval, we should increase our sample size. So for A, we'd want a larger sample size. If we want to decrease our interval, we want a proportion that is further away from 0.5. So here, 0.3 is only about 0.2 away, whereas 0.9 is about 0.4 away. So here, a smaller interval would come from 0.9. And then lastly, we want a smaller interval, so we are going to take the smaller confidence level. And so we did the activity on the previous page, which kind of helps you with this algebraic geometric thinking. But if not, if you just want to skip all the fun stuff, those are your 3 key facts for confidence intervals for proportions. So now, I lost the cursor. Here we go. Let us take a look at the bound on error of estimation of a margin of error, which is the critical value times the statistic standard deviation. So we call this here, this is usually our standard error. Now, all of this, though, this is a standard error, sorry, not the z. But the standard error times z gives us our margin of error, which tells us how far away we estimate p hat to be from the actual value of p. So just as a reminder, for confidence intervals, we're guesstimating. We are trying to figure out what's a reasonable value here for the population parameter. So this gives us an idea because, as we know, our confidence interval is the point estimate plus or minus the margin of error, which is all of this. Now, what if, next page, so how do we actually use the margin of error? Well, the value is used to determine the sample size necessary for which a particular bound on the error is achieved. To determine our sample size, we would need to solve the equation for n. So back to this equation here, sometimes I'm just given a margin of error, but I'm not given a sample size, and I would need to figure out an appropriate sample size to determine this margin of error. So we're actually going to need to break out our algebra skills here in order to find how we could solve for n. Now, because I don't know n, I wouldn't be able to know p hat, because p hat, the sample proportion, counts the number of successes out of the sample size. However, we're in a dilemma. We don't know the sample size, therefore we don't know p hat. So we're just going to assume we know the population proportion, and we'll do that in order to solve for the correct sample size. So suppose we have our equation there, and let's get ready to do our algebra skills here. So I'm going to write this in a different color, maybe? No. So our margin of error equals the z star times the square root of p times 1 minus p all over n. We need to solve for n. Well, the first thing we're going to want to do is divide by z. Oop. Divide by z. And I do not like working this formula out. You also do not need to memorize this formula, but be prepared to be able to algebraically reason your way through it. It has shown up on some FRQ questions and some multiple choice questions. But you're all wonderful mathematicians and statisticians, so this will be no biggie. Now we have the margin of error divided by z equals the standard error of the statistic. Or here, notice that I'm actually not using the statistic because I'm assuming p. So this would be the standard deviation of the sampling distribution. So plot twist. Again, our vocabulary really matters for this unit because there's a difference between parameters, statistics, populations, and samples, standard error, and standard deviation. So back to this main problem though. We need to get n out of there. So we know that in order to invert, right, or get rid of this square root, we're going to take the square. So I'm going to take the square of both sides here. And when I do that, I get the following result. I don't want to change the size just yet. So now I have the margin of error divided by z squared equals p times 1 minus p over n. Okay, well, we're going to do a little bit of a switcheroo here because I need to get n, but n is in my denominator. And all of this here would actually turn into a constant. So what I'm going to do is I'm just going to flip-flop the places here. So it's the equivalent of multiplying both sides and then dividing out both sides. So now I have this, n equals p times 1 minus p divided by the margin of error divided by z squared. Well, almost done here. You could leave it at this point and just plug everything in and then get a value. But what we're going to do is we're actually just going to make this look a little bit prettier, which I know it's difficult to believe, but here goes nothing. When you divide by a fraction, you're technically multiplying by the reciprocal, right? Or KFC, keep, flip, change. So we can find the sample size needed for a better margin of error or a more precise margin of error by doing z divided by the margin of error squared times p times 1 minus p. So this formula here will actually give us, and it's going to fill in, no, perfect. This formula here will give us the sample size. However, since it's a sample size, we usually can't have decimal representations here because we can't have 0.23 right-handed people. We can't have 0.46 of people with brown eyes. We can have that as a proportion, but not as a sample. So what we're going to do is we're actually going to use the ceiling function here, and maybe you've heard of it, maybe you haven't. The ceiling function just says this: whatever you get for your integer value, you're just going to round up to the next integer. So the ceiling function just means if I were to get something like 50.32, I would round up to 51. And so that's just the ceiling function. You can see it's got like, it's almost like a bracket, but it's missing the floor. So let's actually take a look at an example here. And so this is just our conservative estimate. But also, we're not always given p because we don't always know information about the proportion. So when we're not given p, we're going to use a reasonable estimate, and our conservative value here is going to be 0.5. And we do that because, remember, we know that 0.5 times 0.5 will maximize it. So assuming that we don't know, we're going to assume that it's 0.5 because that's just literally smack in the middle, but that would maximize the value of the interval. And then as we acquired more information, we would be able to get a better estimate on the p. So let's take a look at an example here. Let p represent the proportion of students at Purdue University who purchase textbooks over the internet. How many students would have to purchase textbooks over the internet if we wish to be within 5% of the correct estimate with 95% confidence. So we would take our point estimate plus or minus 5% with 95% confidence. So back to the formula here. Of course, you could just start from the general margin of error and work backwards, but we already did this painful algebra, might as well use it. We need our knowns. So here, 0.95, I'm going to go back to the table. Oh, there's my screencast account. Here at 0.95, our z value will be 1.96. So I'm just going to label my knowns here. So I know that z of 0.95 is going to be 1.96. We know our margin of error is to be within 5%, so not 5, but 5%, or 0.05. And we know also, actually, we don't know p. So just as a conservative estimate, we're going to assume p is 0.5, that we can say 50% of students purchase their online textbooks. So now we're going to use our formula. So n equals z divided by the margin of error. So I'm going to do 1.96 over 0.05. We're going to square that. I'm going to assume 0.5 and then 1 minus 0.5. And again, if you're just utterly lost in what I did here, I'm just using this formula with these variables instead. And when I compute this in my handy dandy calculator, I get a sample size of approximately 384.16. However, I cannot have 0.16 of a person. So the needed sample size, of course we want context, the needed sample size would be 385, what? Elephants, cookies, sticks of dynamite. How about 385 students? Not as exciting as a stick of dynamite, but still pretty thrilling. So that's just some examples here on how to find the sample size when just given a margin of error and a few bits of information about your population and sample, as well as some properties of the confidence interval for a proportion.